Our next two lessons are going to deal with what we call combinatorics. Combinatorics is simply a fancy name for counting the number of ways we can arrange things. For example, how many ways can we arrange numbers to get a combination or a code to get into your locker? Now, there's two different categories of the way we can arrange things. First of all is if the order of the things matters. If I'm going to choose contestants from an art contest, first, second, third place, it matters what order I choose people in. If I'm going to select the code for your locker, the order I put the numbers in matters. 12, 15, 32 is not the same as 32, 12, 15. When the order matters, we call that a permutation. Permutation is when the order matters. If the order does not matter, if I'm going to select candidates to run for president, and I say, okay, we have Mitt Romney, Ron Paul, Barack Obama, and Jill Stein, and Gary Johnson. The order I list them really doesn't make any difference. If I'm going to choose students to go to Darien Lake, maybe I'm choosing 10 students, it doesn't matter what order I choose those 10 students. We're all going off to Darien Lake, and it doesn't matter who I called first or who I called last. When the order doesn't matter, we call that a combination. Now, today we're going to be concerned mostly with the permutations. Permutations is where the order matters. And within these ideas of combinations and permutations, there's a mathematical operation that you may or may not be familiar with. That operation is called a factorial. A factorial almost makes you think you're going to English class. It's an exclamation point, but it's not quite the same. Here you have 6 with an exclamation point. That's not 6, like really excited. It's 6 factorial. And 6 factorial means 6 times 5 times 4 times 3 times 2 times 1. And we multiply those numbers together, we get 720. So 6 factorial equals 720. If I had 900 factorial, well, I'd have 900 times 899 times 898 times 897, all the way down to 1. So you can see how it's certainly easier to write something like 6 factorial than all those numbers out, or a number that could get very large very quickly. The one little oddity about these is the number 0 factorial. 0 factorial is automatically said to be 1. Some say that's because, well, there's only one way to arrange nothing. I guess it's open for debate. Now, there's some examples in the packet. Let's try those next couple of examples. Please pause here, and then let's take a look at the solutions. In example A, they ask us to find the value of 4 factorial. 4 factorial is 4 times 3 times 2 times 1, which is 24. In B, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. Numbers starting at 6 going all the way down to 1, and we multiply those together to get 720. Example C and D involve some division. 6 factorial over 4 factorial. Notice on the top the 6 factorial, the 6, 5, 4, 3, 2, and 1. The 4 factorial, the 4, 3, 2, and 1. Notice the 4, the 3, the 2, and the 1 all cancel out, leaving us with 6 times 5, which is 30. D is very similar. On the top we have 49 all the way down, and on the bottom we have 46 all the way down. The numbers 46, 45, 44, 43, 42, all the way down to 1 cancel each other out, leaving only 49, 48, and 47 in the numerator, which is valued at 110,544. The heart of combinatorics involves arranging things. In this example, we have 4 students and we want to line them up. And it says, how many different ways can we line them up? So suppose we have Tim, Bill, John, and Sue. Well, in the first bar, I could put Tim, John, Bill, or Sue. I could pick any of the 4 of them. Suppose I pick Tim. Well, now I have 3 more people left. I could pick any one of the 3 for the second spot. I'll pick Sue. Now I have 2 people left to choose for the 3rd spot. I pick someone, and I have 1 person left for the 4th spot. So this is 4 times 3 times 2 times 1. That's our counting principle back again. There's 24 ways that I can arrange 4 people in a line. Now, because repeats are not allowed, I couldn't put Sue in 1st and 3rd spot. doesn't make sense, we can write it using this special notation, 4p4. This is what that notation really means. The number in front of the p is how many people, in this case, I had to pick from. The number after the p says how many I was going to pick. So I had 4 people, and I picked all 4 of them to put into the line. And the p simply means permutation, that the order matters. And so we have 4p4, meaning we have 4 people to choose from. We're going to arrange them, and we're going to pick 4 of them. Now, this notation only works if you cannot repeat. If I could put Sue in 2 different spots, then I cannot use this notation. We'll actually see an example like that in just a couple of moments. But before we go there, please pause here. There's a few examples for you to try. Give those a shot, and let's take a look at how you do. So now let's take a look at evaluating some of these using what we know of the notation. Number 5, we have 5p5. That means we're going to select 5 different things. And so we have 5 things to choose here, 4 to choose here, 3 to choose here, 2 to choose here, 1 to choose here. 5 times 4 times 3 times 2 times 1 is 120. Number 6, we're going to choose 2. We have 7 total. We're going to choose 2 of them, and we have 7 to choose for the first spot, 6 to choose for the second spot. 7 times 6, 42. Finally, number 7, 48p2, we're going to pick 2, and there's a total of 48 that we're choosing from. So we have 48 to pick from for the first spot, and we have 47 to pick from for the second spot. 48 times 47 gives us 2,256. Finally, example 8. How many different ways can we arrange the letters in the word math? 4 times 3 times 2 times 1, 24 ways. So what happens if things can repeat? Does it really make that much of a difference? If, for example, I want to create a code, I have 5 letters, A, B, C, D, E, and I want to create a security code, well, let's take a look. Suppose I want 5 letters, and I can use them as many times as I want. I could use A if I wanted to, A, B, etc. Well, the first one, there's 5 to choose from, A, B, C, D, or E. The second one, there's 5 to choose from, A, B, C, D, or E. And in fact, there's 5 to choose for the third, the fourth, and the fifth, because I'm allowed to repeat the letters. Counting principle says multiply them up. There's 3,125 different arrangements I could make, or different codes I could make, that would use these 5 letters. Now, suppose I wanted to be a little more picky. Suppose I said we're going to use A, B, C, D, E, but you can only have each letter 1 time in your code. So once you use an A, you can't use it again. Well, that's a little bit different. Now, letters can't be repeated. The first one, I have 5 letters to choose from, A, B, C, D, E. I pick one of them, I put it there. Now, for the second number, I have to pick from 4. There's only 4 left because I can't use any of them over. Third one, there's 3 left. Fourth, I have 2 to choose from. And the fifth spot, I only have 1 letter remaining. 5 times 4 times 3 times 2 times 1 gives me 120 different codes that I could create. So by not repeating the letters, I have a much significantly smaller number of codes that I can make. Now, up here, repeats were allowed. I could not use my fancy notation. But down here, because I cannot repeat, I could use 5p5. There are 5 letters, and I'm going to pick 5 of them, and the order matters, because the code ABCDE is different than ABCED. And so this is the basics of combinatorics using permutations. Now there's a few more examples for you to try in the notes. Let's take a look at those. Let's pause here, and let's see how you do on those. Example 10, we have 2-digit numbers being formed using the digits 1 through 6. If repetition is allowed, we have 6 digits possible for the first spot, 6 digits possible for the second spot, a total of 36 numbers. If, on the other hand, the repetition of digits is not allowed, no repeats, We have 6 choices for the first spot, 5 for the second, giving us a total of 30 possible numbers that we could make using those digits. Finally, let's suppose we have a couple more criteria. C says the repetition of digits is allowed, meaning we have 6 possibilities for the first spot, and the number is even. Well, that means the number has to end in 2, 4, or 6, giving us 3 choices. So there's 18 even numbers we could make given repetition. If repetition is not allowed, then we have odd digits, meaning it has to end in 1 or 3 or 5, and that leaves 2 digits left for the first spot. So we have 2 times 3, which gives us a total of 6. Finally, on the last page of our notes here, we have a 3-digit number being formed by the digits 1, 2, 3, 5, 7, 8, 9. 7 digits. We want 3-digit arrangements. We see example A with repetition allowed, 343. B with no repetition allowed, 700 times 6 times 5, 7 times 6 times 5, 210 numbers. Example C says the number has to be less than 500, meaning the digit in this first spot here has to be 1, 3, or 2. That leaves us 7 and 7 for the last 2 spots, but only 3 possible digits for the first spot. D says the number must be less than 500 and repetition is not allowed. Again, that leaves us 3 possibilities for the first spot, 1, 2, and 3, 6 to choose from for the second, and 5 to choose from for the third. A total of 90 numbers would meet that criteria. And here we see the very last one. We have a contest, and we have 50 entries. We're choosing 3, 50 times 49 times 48, 117,600. You can very easily calculate permutations and factorials using the TI-84. On the TI-84, everything you want is under the math function, which is located right under the alpha button. If you arrow over to probability, PRB, you'll see a whole bunch of things. Number 4 is your factorial, and so if you want the factorial, you could put, for example, 6 factorial. So 6, I'll go into the math button, over to probability, pick the exclamation point, the factorial, and it calculates that for you. If you want to do your arrangements with permutations, again, same thing. You're going to go into the stats section in the math button. So let's say we have 10. We want to pick 5 of them. So we have 10, P, 5. And we get the P by going over to probability and NPR, 5. And so we have 10. It's a permutation. We're going to pick 5. There's a total of 30,240 ways we can arrange 5 things when we have 10 to choose from. That's how you can do this using the TI-84. Now let's take a look how we can use the TI-Inspire to calculate our factorials and to count our permutations. We begin by starting a new document, and we insert a calculator page. And we want 6 factorial. So all we have to do is type the 6, select the menu, go to probability, and we see that the first option is factorial. And so now we have 6 factorial typed into our calculator. When we hit enter, we get 720, just as we expected we would. To calculate your permutations, here's how you do that. We go into our menu, and we pick probability and permutations. Notice we did not type any numbers in yet. So now we wanted 10 P5. We go 10, 5. We hit enter, and we have 30,240 different ways that we could select and arrange 5 things from a group of 10. This is how you can do this using the Inspire. And so there you have the basics of permutations. If the order you pick things matters, it's a permutation. We have this special notation we can use if repeats are not allowed. We know that we can use our calculator. We've seen how we can do that. And these are the basics of everything that you need to know when the order you arrange things matters.